Hello, welcome to our presentation. My name is Vimlan Naika. I'm joined by Ivan Burke from Blue Vision ITM and Saad Kari, a master's student at Wits University. Today we will be discussing the fundamentals of cryptography, RSA and ECC, Shor's algorithm, the future of cryptography, quantum-resistant cryptography, and PQC, post-quantum cryptography. We will also be discussing the basics of quantum computing and talking about superposition. Superposition, that's a big term. And entanglement, another big term. But we want to avoid buzzwords such as quantum supremacy, wormholes, time travel, and other spooky concepts. For me, this topic is fundamentally about change. Change happens through evolution or revolution. Evolution happens slowly. We know what we don't know. And using the scientific method, we find out what we don't know. A good example is Moore's law. We know that the capacity of the CPU can be increased over time. We just need to figure out how to do it. A revolution, on the other hand, is completely different. We don't know what we don't know. And that's where we have scientific discoveries, scientific breakthroughs. When we discover something new, it's amazing. It changes the world. Like the discovery of penicillin was an amazing discovery. Quite often, scientific breakthroughs are followed by engineering breakthroughs. Quantum computing is currently going through a series of engineering breakthroughs. But the error rates are still too high. Hopefully, the error rates will start dropping soon, and that would lead to the spread of the technology. The theory of how technology spreads is explained by the diffusion of innovations, or DOI model, and UTOT, that's a mouthful, the unified theory of acceptance and use of technology. As an example, the use of electricity in the US started around 1900. It reached 20% in 1915, 65% in 1930, 85% in 1945, and 100% in 1960. It took 60 years to reach saturation. The use of the internet started around 1990 and reached 52% in 2000, 76% in 2010, 90% in 2019, and 95% in 2023. It took just over 30 years to reach close to saturation. The notable observation here is that it took 60 years for electricity to reach saturation and only 30 years for the internet. So that trend continues. The time frames are getting shorter and shorter for new technologies. Although the time frames for saturation are getting shorter, the adoption rate follows a typical bell curve, starting with a group called the innovators, and then another group, the early adopters, which is followed by the early majority, the late majority, and finally the laggards. You got to ask yourself, in terms of quantum computing, which group do you fall under? Hopefully not the laggards. Quantum mechanics and quantum computing may seem abstract to a lot of people, but today we will be presenting the practical uses of quantum computing. To be sure, quantum computers are real and used in real-world environments. There are many quantum computing companies in existence, companies such as D-Wave, IBM, Google, Microsoft, Quantinuum, Rigetti, Atos, IonQ. IonQ does something, a technology called the trapped ion. The Chinese are there with CAS, the Chinese Academy of Sciences, and then the old favorites, Intel and NVIDIA. And these are just the front runners. D-Wave is a company that specializes in optimization, also known as quantum annealing. In Joburg, we have the WITS Quantum Initiative, which is at WITS University, and there's an IBM lab in Juta Street, slightly off campus. We have quite a lot of quantum in South Africa, and Saad will be presenting more on that. Thank you.
Okay. So good morning, everyone, and thank you for attending our presentation. Very quickly, so there's been a realization by a lot of the academic professors that we need a roadmap for quantum in South Africa. And so South Africa's stance has always been to focus more on the software developments as opposed to the actual engineering of quantum, because we don't have enough money for that. So actually there's 5 involved universities. We have WITS, UKZN, Stellenbosch, University of Zululand, and Cape Peninsula University. And our focus is on, as I've mentioned, software. So very quickly, I'm going to dive into cryptography, a very quick overview. So many of us may have came across cryptography working in cybersecurity. So I'm going to run through this quite quickly. So cryptography, simply put, is the science and art of hiding information using various different forms of techniques. So cryptography provides confidentiality, integrity, and non-repudiation. So confidentiality makes sure that the information is only for the intended recipient. Integrity makes sure that the message stays as the message was sent. And of course, non-repudiation allows for individuals to have responsibility. So some of the questions that cryptography answers is, how do we transmit messages securely through an insecure channel, i.e. the internet? How do we keep the integrity of a message? How do we ensure that the message is only for the intended recipient? And how do we prove that we are who we claim to be? So cryptography can be separated into 3 frameworks. Generally, we'll have symmetric cryptography, asymmetric cryptography, and hashing as well. So mathematically, most hashing algorithms are one-way functions, so we're not going to be covering that in today's presentation. Very quickly, symmetric cryptography is the idea of having one cryptographic key per partner. So whenever there's a communication link from one party to another, you use the same key to encrypt and the same key to decrypt. So it's often used for encrypting bulk data and data at rest, and it's a fast form of cryptography that's generally used. Some examples of the modern day cryptography techniques is AES and 3DS. So our presentation will be mainly focusing on asymmetric cryptography. So in asymmetric cryptography, each party has 2 keys. One is called a public key and one is called a private key. It's often quite slow and mostly used to establish session keys and authentication, such as digital signatures and so forth. So it's also generally used to prepare for symmetric key establishment. So very quickly, why do we need public key cryptography, which is another term of asymmetric cryptography? It's because symmetric cryptography has 3 core challenges. The first challenge is a key distribution problem. Of course, communicating to a party and transmitting a plain text key can cause a lot of problems. The second situation is the number of keys per party. That's the second challenge, which is given by the following equation. So essentially, 20 parties would require 1,225 keys if we were only to use symmetric cryptography. And the third example is that there's repudiation. So one example of that is if Alice sends a purchase order to a vendor, she can then change her mind later on and claim that the vendor falsely generated something. So asymmetric cryptography was actually introduced in 1976 and provided a solution for all of these challenges. So in asymmetric cryptography, as I've mentioned, we have 2 types of keys. We have public keys that are available to anyone, while private keys are kept private, as the name suggests. So one rule of thumb for asymmetric cryptography is that public keys are always used to encrypt, while private keys are used to decrypt. So Alice will compute her own private key A and public key F. Bob will compute his own private key B and public key E. And if Alice wants to send a message to Bob, essentially Alice would use Bob's public key to encrypt and then send the message forward. So this solves the challenge, as we've mentioned previously on the slide before this. So in RSA, these public keys and private keys are large integers, which are essentially very long numbers, whereas in elliptic curves, apologies, these keys are coordinates on a curve. Okay, so very quickly, an introduction to RSA. So RSA is fundamentally based on something in mathematics called modular arithmetic, right? So I'm going to go through the first example. It's actually, I'm going to explain it in a simplistic way. So essentially what it tries to do is to find a remainder. So if we have 7 and we divide it by 5, our remainder would be 2. So that's generally how these equations work. So there'll be two parties, Alice and Bob. The way RSA actually works is that Bob will compute his private key and public key, as we've mentioned previously. C, in our case, would stand for ciphertext. In other words, the gibberish that would be sent through the network. M would be the plain text, and P would be the prime modulus. So if Alice wants to send a key, if she wants to send a plain text message to Bob, she would then use the following equation, and once Bob receives the ciphertext, he can then use the following equation from there. So very quickly, an introduction to elliptic curve cryptography. So elliptic curve cryptography is often seen as the bigger brother of RSA, and this is generally what a real elliptic curve would look like, which is a cluster of points. But for explanation purposes, a lot of mathematicians have realized that we could explain these type of curves through the following graph. So for the sake of completeness, elliptic curves are actually plotted over a domain which is referred to as a finite prime field. But for purposes of explanation, we can explain this using a real line. So this is an idea of what an elliptic curve actually looks like. So introduction to elliptic curve cryptography. If you use a specific example, we'll be given that particular equation. So as you can see, if we compare this equation to what we had at RSA, essentially elliptic curve cryptography, it adds pies to RSA, essentially making it more difficult to solve and to break. So there are a few steps that are involved in this process. The first step will be encoding our plain text message, which could be a video, it could be voice recording, it could be anything of that sort. The first step would be to encode that plain text message as a point on a curve. We'll then follow it by step 2, where we'll establish, as we've mentioned previously, a private key and a public key. And then step 3 will then be to encrypt using the following formula and to decrypt using the following formula. So here's an actual example with some real numbers. So this is an example of an elliptic curve. So if Alice has a plain text message M, which is given by 4,5, and Bob has a public key, which is given by T, Alice can then use the following formula, and then Bob can then decrypt and get 4,5 as well. So I'm now going to pass you on to Ivan, which is more practical.
Hi, everyone. I'm just going to be talking a bit about some of the bad implementations that sometimes can lead to issues with these encryption algorithms that was just mentioned by Saad. So I mostly use this type of stuff for cybersecurity challenges. So I set up a lot of cybersecurity challenges for other students or for companies. So one of the popular ones that we did is we give people a partial private key and see how much of the data we can omit from the private key and have them still recover the private key. So this was quite popular, especially around 2012-ish, when a lot of attacks could get you partial data. So for example, Heartbleed, there was a lot of attacks at that time that focused a lot on retrieving partial data from hard drives or from communications. So then the concern was, but how much of a private key would you actually need to recover before you can actually reconstruct the whole thing? So we did a lot of work back then about this. So basically, because it's fairly well documented, the structure of RSA private key, a lot of the data in there is a bit redundant. So if you know the structure, which is defined by ASN, you can go and seek out specific key offsets within the data sets to find where, for example, the first prime, second prime is. RSA mostly works on the principle that two large primes are multiplied together to get you this value n, and n is basically very difficult then to factorize back into its original primes again. But for the private key to work, it needs to store those two primes. So if you can recover either one of those two primes, the other one can be retrieved by just dividing n again by one of the primes, and you get the other prime. So we did a lot of these type of challenges. The CTF that was available for this event also used one of these as an example. Then what other weak implementation is shared primes problem. So because RSA keys, they need to generate a prime, and it's fairly difficult to computationally expensive to calculate a prime, a lot of companies, what they would do is they would take shortcuts. They would choose a short list of primes and they would just reuse them and select random two out of these sets. The thing is, Euclid came up with a formula over 2,300 years ago that can easily factorize this. So this is a couple of thousand-year-old formula, but yeah, so Euclid's formula you can use to, if two large numbers share a prime, you can use Euclid's formula to find one of the primes between them, and then you can get the other prime by just dividing n again by the primes. So Euclid's formula is used for that. So some company, they presented in 2017 at Black Hat. What they did is they turned this into a big data problem, and they started harvesting public keys. Because for this, you don't need the prime, so you just need someone's public key. And the public key already contains the value n, so that's the product of the two primes. So what they did is they just saw how many primes can they collect, and how many of those primes actually share primes, and how many can they then crack as a result of this. So they went and they harvested from GitHub, from all the sources, because that's sort of the thing. You want to share your public key. Remember, your private key you want to keep secret, but your public key you want to make as widely available. So they collected from PGP, they collected from all kinds of sources, and they collected about 220 million keys, and they had about 65% of the keys they harvested they could crack again. So they literally just turned this into a big data problem instead of a security problem. Yeah. And then another bad implementation that's fairly common is if they use what's known as a Mercer prime. So Mercer prime is basically 2 to the power x minus 1. That tends to be a prime. So a lot of companies, what they would use, if they just want a quick way to generate a prime, they'll generate the Mercer number and then just validate if that's a prime. If that's not, they just increase 2 to the power x plus 1. And they go on with this until they find a suitable prime. But those primes are very easy to look up for a computer, very easy to crack for a computer. So if your algorithm uses a Mercer prime to generate its two primes for a private key, that can lead to security vulnerabilities. Another implementation would be if you're vulnerable to the Format's algorithm. So Format's algorithm, that tries to determine if your two primes are fairly close to each other, then the easiest way to find one of the two primes is to get the root of n, and then just go to the roof of that, and then test if that's a prime. If it's not, increment by 1. If not, repeat this process until you find it. If the two primes are fairly close to each other, this is a very trivial problem to solve, and it's like the algorithm is right there. It's 4 lines of code. So it's very nice. I think one of the challenges this year was also based on that. Yeah. So I'm just going to hand back to Saad to explain the rest of quantum.
Thanks. So I've just got 2 slides here just to give you a little background of how we get to quantum computing. The binary principle is the foundation of all modern computers. When we look at the history of modern computers, we will see that it started with the punch card. You have a hole, no hole. Simple binary principle. Building on the binary principle was vacuum tube computers in the 1940s. You had 2 possible states, on and off. Another example, have you seen this? CD. So have a bump, no bump. If you look closely, you'll actually see where there's bumps and no bumps. So I went onto the net looking for punch cards. I thought I'll do a little show and tell, buy some and pass it out to you guys and, wow, you guys. But then I found this in my locker and I said, I'll save all that money. I'll just show you guys this. You can actually touch it. It won't break. Yeah, absolutely. I'm not young. I had my mustache dyed, by the way. So generally speaking, we have 2 distinct states. That's the binary principle, and it's served us well for over 100 years. So the transistor can be considered as one of the greatest inventions of the 20th century. The first CPU had only a few thousand transistors. That has evolved to billions of transistors today, and continues to evolve, still following Moore's law. This brings us to the fundamental difference between classical computers and quantum computers. Classical computers follows the binary principle. You have two distinct states. In the transistor, you have a high voltage and a low voltage. Quantum computers use something totally different. It uses the concept of superposition. That is huge, as I said earlier on. Saad will be speaking about that just now, but I just wanted to go through some of the logic gates. So in terms of logic gates in a classical computer, again, it uses the binary principle. You have your NOT gate, your AND gate, your NOR gate, your NAND gate. There's quite a few gates. And then you obviously can combine those gates and you have different type of computation. In terms of quantum computing, the quantum logic gates include the Hadamard gate, the Pauli or Pauli X gate, the Pauli Y gate, the Pauli Z gate. You have the controlled NOT gate, and the list goes on actually for quantum logic gates. I'm just giving you these terms because you will be coming across these terms. So you're not only talking about NAND gates and your basic building blocks. The Hadamard gate at the moment is, a lot of people use it for, as I spoke about D-Wave earlier on, for optimization. The Hadamard gate is one of the most common used quantum logic gates. Saad will explain the basics of superposition and quantum computing.
Okay, so very quickly as a revision, in classical computers, the zeros and ones effectively don't represent anything in nature, right? So the zeros and ones are mathematical representations of high voltage and low voltage. So what exactly is a bit and how does it affect us in application? So essentially 2 bits, if we use 2 bits, we can have 4 possible combinations. We can have a 0, 0, 0, 1, 1, 0, or a 1, 1. So that would mean that we require 2 bits of information in order to describe it. In other words, if I were to say choose one of the 4 possible combinations, you would have to give one value followed by a second value. So we'll see later on in the next slide how that's going to differ with quantum computing. So a classical computer would have to also compute each possible combination individually as opposed to how quantum computers work. And it will make more sense as we progress. So quantum computers are built on 2 primary principles. We have the quantum entanglement and we have superposition, right? So, I mean, we can just ignore the notation of the straight line and the incomplete triangle, but essentially we can represent a qubit state by phi. So we're using the same idea of the binary digit where we had zeros and ones, but just now in a different notation, right? So as you can see, we have A times that 0 plus B times that 1, whereby if we take the modulus squared of A, we get the probability of an electron being in that particular state. So in other words, our qubit is essentially at both the 0 and 1 simultaneously. So if you look at the diagram, if we make 0 represent purple and blue represent 1, you can actually see that at any given moment in time, you can't distinctly say that the electron is at a 1 or it's at a 0. It's effectively at both at the same time, which is a bit counterintuitive, but it ends up working, right? That's quantum physics, which has been scientifically proven and is a natural phenomena. So a 2-qubit state system can be represented by the following equation. And then, as I've mentioned previously, we'll touch on a little bit on entanglement and superposition. So I know this is a very bad-looking curve, but essentially, if we make the y-axis our probability, just to explain superposition in a different manner, if we have positions A and B, then we have a probability curve. That's how the quantum physics explanation is described. So what is the chance of an electron being at position A as opposed to being at position B? So if you look at the curve, you can more or less say there's a 70% chance of it being at A and a 30% chance of it being at B. So at the end of the day, even though we have these superposition principles, we have to come back to classical computation because we need to solve classical real-world problems. So then we utilize something that's called a collapsing of a state. So it turns out whichever position you measure the electron at being, if, as an example, as depicted, if we measure the electron at being at position A, it will then end up only being at position B for the rest of the time. And if we end up measuring the electron at position A, it will only remain at being at position A. So all of these principles are utilized in quantum computing through the use of quantum engineering to allow us to solve real-world problems. So how qubits are measured? So if you consider 2 qubits, as we've mentioned previously, but now with some real numbers, if you describe the first qubit by phi 1 and the second qubit by phi 2, essentially in quantum computing, you have to define things as a system. So we don't deal with each classical bit individually. The more qubits you add into the system, you have to describe them relative to each other. So due to entanglement effects, which basically, to give a practical example, if we had to prepare 2 qubits in entanglement right now, we could send 1 qubit to Mars and have the other one here, and essentially whatever happens to the qubit in this room would directly and simultaneously happen to the other qubit at Mars. So gets a bit more crazier than that, but essentially, so we can see if we have 2 qubits, 2 separate qubits, and we want to bring them together, they're then described by phi f in the following manner. So the point that I was making at the slide is that if you look at the 0 from phi 1 and the 0 from phi 2, we can see that we multiply 3 over 5 by 1 over square root 2, which gives us 3 over 5 square root 2. So essentially, the final state depends individually on every qubit. So if we have a quantum computer with 100 qubits, every qubit has to be described relative to the other 99 qubits. That's partly the reason as to why it's so difficult to build these quantum computers, and also partly the reason as to why we can compute things quite quickly. So m qubits require 2 to the power of m bits of information in quantum computing, whereas classically n bits require n bits of information. So as we've shown earlier in the first slide, one example of this would be 3 qubits. So in order to describe 3 qubits, we would need 8 bits of information, whereas classically 3 qubits you would need 3 bits of information. Or to use a smaller example, as we've mentioned earlier, for the 2-bit situation, we required 2 bits of information to be given, because we had 0, 0, 0, 1, 1, 0, or 1, 1. So we'd have to give 2 values. Whereas quantum mechanically, as you can see from this equation, we have to describe 3 over 5 square root 2, and the second 3 over 5 square root 2, then the 4 5 square over 2, and the 4 over 5 square root 2, which is for a 2-qubit system. So quantum mechanically, a 2-qubit system, you need to provide 4 equivalent bits of information. So if there's anything to take away from those slides, it will be this last line. So essentially, 9 operations to find something classically versus a maximum of a square root of n times on a quantum computer. So to put this into perspective, if we had a bag with 100 balls, and the question is, which of those balls are blue, a classical computer would have to individually solve for each and every single ball. So that would be 100 times, because there's 100 operations. Whereas for a quantum computer, that would be the square root of 100, which is equivalently 10. So solving the same question, on classically, we had 100 operations. On a quantum computer, we can do that. We can get the same answer with as little as 10 operations. So I'm now going to pass you on to Ivan.
Hi. Yeah, so I'm going to just quickly talk about Shor's algorithm. So before I do that, I'm just going to explain how you decrypt, again, a RSA key after you've now gotten to 2 primes. So over there, you'll see there's 3 basic steps that you need. So first, you need to calculate the theta of n. So the way you do that is basically you get P and Q, or P minus 1 times Q minus 1, and that would be the theta. And then you put that into the inverse of B to get back your original message. So this is basically just, it's a lot of maths, but it's basically just to explain to you that you need P and Q once you've got your encrypted message to get back to your unencrypted message. So to get back to your plaintext message, you need P and Q. And that's the sort of the problem that you're trying to solve with trying to crack RSA cryptography is because P and Q is quite difficult to get, because N is very difficult to factorize. If you can get either P or Q, you can follow these steps basically to get back to the original message. So what Peter Shor did is he developed this in 1994, so that's 30 years ago. He came up with this idea, and this is more based on numerical theory. So instead of trying to calculate this out of a physical machine, what he did is let's look at the properties of numbers and how numbers interact with each other, and what type of properties you can deduce from certain behaviors or certain patterns you can observe. So one of the things that we observed is if you're looking for a shared prime between a shared prime between two large numbers, one way that you can do that is represent them in the following way. So in his theorem, so he's got 3 theorems in total. We're only going to be focused on the first theorem. The second and the third theorem more focus on ECC cracking that. The first one is more on RSA. The first theorem basically states that if you're looking for a different way to basically represent a shared prime between these two values, you can multiply either one of the two numbers with each other, with itself, as many times as you want, and eventually that will equal to m times the second number plus 1. So the reason he does this is he's trying to guess what is one of the two primes. Because remember, when you start off this exercise, you have no idea what either of the primes is. But using this algorithm, you can guess a value. And this will actually give you a very good approximation of what one of the primes might be. So your guess will then be plopped into this formula. And if you do a bit of manipulation, you can see you get down to the equation a to the power p equals mb plus 1. So if you simplify that, you can convert that to the difference of two squares. So in this example, I'm just going to show you some examples of where I basically said, okay, so in the first example, for example, there's a and b. So I'm looking for a shared prime between 7 and 15, where that would fit in. So 7 squared equals 3 times 15 plus 4, so that one doesn't work. So you try each example until you get 7 to the power 4 equals 160 times 15 plus 1. So there you find out, okay, now I can get a shared prime from that, right? And then if you put that back into his formula, you can say, I can now work out the difference of two squared numbers. So if you go, so if we take the first example, 7 to the power of 4, so difference between two primes basically is you say, the difference between two squared numbers, you take the root of the first number minus 1, and then the root of the first number again plus 1. So, so for that, you'll see on the right-hand side, that's the formula for that. And using this type of maths, you basically prove that no matter what number you can pick any number at random, whether the number is bigger than one of the primes or smaller than one of the two primes, you still have a 37.5% chance of getting to a better guess. The only situation where this won't work is where either the number you guessed itself shares a prime with the two numbers, or if it's a multiple of either of the two prime numbers. That's where you sort of run into problems. So just to make it a bit clearer, I figured I would show you a bit of a graph about this. So this is now, for example, here I'm looking for another example, and I'm guessing 31. And as you can see, each time I write down what is the error rate. So in other words, what is the remainder? I'm looking for a remainder of 1, but every time you'll see in the first iteration, the remainder is 13, then 4, then 19, and then finally I get to 1. Then it goes to 10, then 16, then 13, then 4. So there's a repetition. So the nice thing about this repetition is that forms a waveform. So as you'll see on the right-hand side here, I represent this as a waveform. And with quantum computing, you can do what is known as a Fourier transform of that waveform. Sorry, next slide. And then you can figure out how frequently this repetition happens. The problem with quantum computing is once you do the measurement, you collapse the states, then you don't know so for example, over here, once you do the measurements, you might get to the state where the exponent was settled to the value of 3, for example. And then you don't get the value that you actually wanted. You'll get, say, for example, then the remainder is 13. But you wanted the remainder to be 1. But because there's a a waveform that basically expresses how frequently the value will be 13, you know what is the max distance that this will basically be. And this max distance will always be the same because there's always a sort of a repeating pattern, right? So you actually just want to know how frequently do I get even the wrong answer. So using quantum computing, you can even get the wrong answer, but because of the properties of it, you can deduce the correct answer due to the collapse state. Because you know that if you know how frequently it gets the wrong answer, then you can know what is the distance between those 2 points. And then you know, okay, this is how many times you actually have to do that operation. So it's sort of working more of a side effect of quantum computing than working with quantum computing directly. Yeah. So over here, sort of more the exact formula. So on the top left-hand side there, you'll see the exact formula, basically how it works. So for this to work, you would need quite a lot of qubits. So for example, if you have a 256-bit key, you need at least double that many number of qubits. So then a 512 qubit system to try and calculate it, because you need at least 2 waveforms to be completed. Because with a single waveform, they might be, due to some interference with it, you might have an offset, might make it go wrong. So you need at least 2 waveforms to complete for it to have a reasonable chance of actually being accurate. We'll later get into the whole how accurate is, because there is some interference that can occur, but basically that's how many qubits you'd need to solve this. So you can imagine if we're now already at 2,000 bit keys, then you need 4,000 qubits, and we're still quite a bit away from that. But using this formula, you can basically prove that you can calculate any of these. You can basically square any large number in as much as 4 operations, because it's basically because all these operations happen at the same time. Because as soon as you collapse it, that's it. You measure it once, it's done. So you went from trying to calculate this with a classical computer with brute force through many, many iterations to 4 quantum computing state calculations that you basically have to do. And you have a 37.5% chance to get it right on your first try, and within 5 tries you have a 99.999 chance to get it right. So it just shows you how much quantum computing actually speeds this up. And now it's going to finish about the future of quantum computing. Yeah.
Okay, so essentially what we've established in this session is that theoretically speaking, modern day encryption is proven, or is theoretically proven to be broken by quantum computers. That's essentially what we've explained. And it's just a matter of the quantum computers catching up to reach the correct number of qubits. Once that's reached, it's proven that modern day encryption would essentially break. So since we use encryption in almost everything that we do in our daily lives, we use encryption to surf the internet, we use encryption in WhatsApp messaging, we use encryption in banking. So of course they have to propose new ideas as to how we should move forward. So effectively, NIST, which is an organization which regulates cryptographic algorithms for the world, have opened a challenge previously to mathematicians of the world to propose new ideas as to what type of mathematics to use. So from that challenge, there were 66 submissions that were made, or approximately 66, and 4 of those submissions have been accepted by NIST. So we have Crystal Scriber, Crystal's Dilithium, Falcon, and Sphinx Plus. So essentially why this is proposed to work is because now the mathematics has changed. Generally speaking, most of these solutions follow what we call lattice-based cryptography. So as we can look from a few screenshots with a simple Google search, we can see that there are a lot of different companies which are already adapting to these post-quantum methods, such as Zoom as an example. So this has of course been a major concern for the world. So this is one methodology of moving forward in order to solve the problem, which is a traditional mathematical way. So take out the existing algorithms that you use and then implement these following algorithms. However, we do also have a physics solution, which is generally used by by companies or organizations within the military or something of that nature. So what happens here is that communication is done through the use of photons. and it utilizes the effects of quantum physics so that whoever is on the line or whoever tries to decrypt information can never do that based on the hardness of quantum physics. So the idea of quantum cryptography and quantum key distribution actually started with the BB84 protocol, which was developed in 1984. It then moved on to the B92 protocol and then the E91 protocol. So quantum cryptography is also used for satellite communication. In fact, in China, that's their means of communication between the ground and between the satellite and between various satellites, as you can see from these Google searches. So that would be the end of the presentation, and thank you a lot for paying attention. If there's any questions, then... Oh.
So two questions. The first one is, when it comes to the probability waveform collapse on observation or measurement, how do you know whether or not you've got interference? Are you effectively running 3 or 4 of those in parallel and then using that as a probability distribution amongst the 3 different computations?
Okay. So how it currently works is that's why they say you need at least double as many qubits as the key length. So your first indicator that there might be an error is if those 2 waves don't repeat like that. Like I said, it's supposed to be a perfect repetition. If it doesn't repeat properly, then you have your first indication of a fault. And then obviously your second way of doing it is if this says that is a shared prime and you look out, because that's literally just a calculation, you just go n divided by that number. If that isn't a shared prime, that would also indicate for you that. But your first indication would be that there's a discrepancy between that waveform. That would be your first indicator.
Okay, and so then you're running the fast Fourier transform on top of that?
Yeah.
Okay, cool. And then the second question is really like, how can cybersecurity professionals protect themselves? It seems like what you're sharing here, just based on the complexity of the key length, is that increasing your key length to absurd numbers might be a real good way to, at the very least in the short term, make it more difficult for the store and decrypt strategies, and then in the long term, is it then moving to a Swing's algorithm or something like that that's easily implementable?
Yeah, so I think we'll both cover that question. So essentially, the amount of key length in RSA and ECC hardly has an effect when it comes to the quantum computers breaking it. However, in symmetric cryptography, so there are cryptographic levels of security that are used to measure the secureness of an algorithm. So something like AES is actually mathematically more secure than asymmetric cryptography, but now they're 2 different forms of cryptography. So in terms of something like AES or 3DS, if you increase the key length on that side, it will make it essentially a little bit more difficult for a quantum computer, but not to say that it's not possible.
Okay, cool. So the answer is switch to a quantum-resistant technology as soon as possible.
Essentially, I guess that's why. So NIST is working towards regulating it, and quite close to the final stages of passing it out in the public.
And in our example, we specifically just now talked about RSA because that's probably the easier one to explain. With ECC, as I mentioned, you need about double as many qubits as the key length. For ECC, you need about 6 times as many. So ECC is already like levels above that, and so the current largest
300 and something for ECC, or 600 even.
Yeah, but the current largest quantum computer, what's its size? It's how many qubits?
1,000 something.
Yeah, it's about 1,000 is the largest. But even that one, there's lots of caveats about in an ideal situation, when everything works perfectly well, it has 1,000 qubits. Yeah. So we're still quite a bit away from that. But the thing is, what we're trying to just say is it will eventually happen. So that technology is getting there, but it's still going to take a while. So having logic key will help to that degree, but you're just delaying the inevitable.
Gotcha.
So having something that's quantum resistant is a bit more of a longer term solution than just increasing.
Gotcha. So that effectively means if you're taking the 1024 qubits divided by 2, we're looking at asymmetric encryptions at 512-bit being assumed to be decryptable today.
Absolutely.
Right.
In theory.
In theory, yeah.
But just to add to your point, so I had on my slide, I didn't touch on it too much. There's the concept of harvest now, decrypt later. Yes. And a lot of governments are already doing that. So if you are running 512 now, and theoretically we got 1,000, but I remember I spoke about the error rates are very high. So in the lab, they're getting the 1,000 qubits to work, but you cannot make it work in production, basically. So it's in test, basically. So harvest now, decrypt later. So be careful what you're doing right now, because 5 years' time, the guys can decrypt.
Especially at the 512 bit rate.
Absolutely.
Yeah. Gotcha. Awesome.
So yeah, okay. Whoever gets the mics first. There's 2 hands here.
Oh, there's one for you as well.
So follow the mic.
Is it on? A very quick question. Roughly estimated, how far off are we before we get to like 4,000 qubit machine?
No, we're not going to prognosticate on that. Yeah, absolutely.
So that's actually the hot topic. There's differing opinions depending on...
I covered that in my opening remarks. We're not going to talk about that, yeah.
Yeah, so there is, I mean, a lot of differing opinions. Yeah. Okay, are we skipping?
Yeah.
Okay.
So this is just a bit of a follow-on from the question of the first gentleman. But so I was fortunate enough to partake of the CTF, so thank you for that. But during that research, I saw the cryptography challenges. And part of that was seeing that AES, I'm not sure how accurate this information is, but apparently AES is considered to be quantum resistant. And I just wanted to understand what is the difference between something like that and what you've shown us here, like, for example, the Christos-Kuiper algorithm. And is it getting to a point where, as a security professionals, for us to protect these systems, are we actually going to need quantum computers to do the encryption? Like, will classical computers no longer be sufficient at some point?
Okay, so firstly, what makes AES slightly better than RSA is RSA is heavily dependent on these primes and the factorization of these primes being difficult. AES doesn't use that. So Shor's algorithm is specifically developed to try and factorize primes. So to our current knowledge, there is no similar algorithm for trying to decrypt anything that uses like a block cipher or anything like that uses AES.
Yeah.
But
Grover's algorithm.
Oh, Grover's algorithm, yeah. Okay.
Yeah.
You know.
So my question is sort of more physics, I guess engineering based. What are they doing currently to induce state on qubits? And physically, what's the difficulty of collecting a lot of qubits? Do they collapse if there's too many of them? And how do they induce state? Is it a modified Stern-Gerlach? Are they still doing that?
Yeah. So that's more of a quantum engineering question, more of the electrical engineering. But essentially, I mean, they still use the semiconductor chips, right? So even in quantum computing. So they would use a semiconductor material that's something like silicon, which is made up of isotopes. We have silicon-28, silicon-29, silicon-30. So essentially that would provide a vacuum in which phosphorus atoms are actually doped into that. And then essentially they use a similar analogy to how it's done classically, where we have a transistor. But what tends to happen is that we'll have a source and a drain, and then whenever an electron falls onto the transistor, it reaches through various different means, mainly through magnetic resonance that's used in order to change the probability. Because so you can actually apply magnetic resonance to manipulate how probable you want a 0 or how probable you want a 1. And then you reach a stage where the electron is both off and on the transistor at the same time. That's essentially where the superposition comes from. Yeah.
Thank you. Are there any other questions? One last one.
Sorry, I felt like this part of that question wasn't finished. I think he asked what would make some of the quantum resistant algorithms, what actually about them makes them quantum resistant? And then I think he did ask, do we need quantum computers to be able to do the encryption for normal systems to keep them quantum resistant for like attackers?
Okay, so the first question is the mathematics of post-quantum cryptography has nothing to do with modular arithmetic anymore. It's essentially, as I've mentioned, lattice-based cryptography, which is more algebraic, it's more dimensional. So it's taking problems and it's adding more dimensionals, which makes it significantly more difficult to solve. So essentially, mathematicians have used creativity to get away from the problem that we face. And then the second question, no, you wouldn't need a quantum computer in order to do encryption. It's just that the way the quantum computer works, you can design your mathematics in a way which doesn't give an advantage to a quantum computer. So there's mathematics solutions and then there's physics solutions, but those are a bit impractical because you physically send through light beams in order to communicate, or through optical fiber as well. Yeah.
One last question. Are we in between you guys and lunch?
Okay.
Not yet.
There's one more talk.
Oh, there's one more talk, okay.
Hi. I just wanted to ask, in terms of the hardness between RSA and elliptic curve cryptography, is it based on the discrete logarithm problem between the two?
Yes, essentially that's what it is. It's just that elliptic curve cryptography is more efficient, significantly more efficient. So as we've seen, if you look through directly from the equation, what elliptic curve cryptography just tends to do is that it takes a basic like m to the power of e and makes it a polynomial. So actually, like a 256-bit elliptic curve is as secure as like a 2000-bit RSA key. But the hardness of the problem is based on modular arithmetic. And one example, just to get it through, is if you look at a clock, right? So if I say it's now 12 o'clock, and later on it's 1 o'clock, how many hours have passed? So if I don't specify if it's AM or PM or which day it could be, someone could say 1 hour, someone could say 13 hours, and so on and so forth. So the idea of modular arithmetic is that there's a very large set of possible answers, and that large set is quite significant. So for a classical computer, it would in fact take thousands of years to just break and go through one algorithm. So it's based on the idea of modular arithmetic, yeah. I don't know if that answers the question.
Yeah.
Okay.
Thank you, guys. I think we'll have to wrap it up. We're over time. Thank you.